In mid-July 2026, a series of viral posts claimed that loop engineering was dead, replaced by a new discipline called graph engineering. The posts cited a $3.1 million joint study by Stanford and Anthropic that does not exist. It was engagement bait, designed to capitalize on a rapidly shifting technical landscape. The AI development space has spent 2 years on a terminology treadmill. Builders moved from prompt engineering to context engineering into agent harnesses, and finally settled on loop engineering as the standard method for automating language models. The current noise around graph engineering stems from a core industry error. Practitioners are taking 3 distinct computational architectures and conflating them into a single buzzword. The first structural layer is orchestration state. This dictates how an autonomous agent structures its execution steps, mapping out parallel tasks, sequential dependencies, and fallback paths. The second is control topology. This governs how a network of autonomous systems measures its own success, preventing individual agents from optimizing their internal metrics at the expense of the overall system. The third is typed knowledge. This dictates how an agent retrieves and navigates causal memory, allowing it to trace logical reasoning across thousands of interconnected documents. Moving from loops to graphs establishes programmatic boundaries across execution, evaluation, and memory. Through early 2026, most AI agents operated on a simple plan, do, check, act loop. A model executes a task, an internal verifier checks the result, and if it fails, the task routes back to the start. The critical vulnerability here is that the verification step runs inside the same context window as the execution step. We call this the context swamp. Raw HTML, executable code, and half-written prose collide in a single context window. A self-reviewing agent operating here is equivalent to a student grading their own homework with the answer key open. An orchestration graph solves this by splitting the workload across a directed acyclic graph. Instead of pooling in one prompt, programmatic state flows along explicit edges between isolated nodes. This provides strict context isolation. The writer node only receives structured notes. It is never exposed to the raw search HTML processed by the researcher node. The reviewer node operates in a clean context. It evaluates the final output against success criteria, carrying zero memory of the drafting process that preceded it. By utilizing explicit routing along these graph edges, developers can program deterministic control over parallel execution and define fallback paths for when an agent fails. Orchestration graphs encapsulate loops, protecting the integrity of the agent's context window from degrading over time. When you scale from a single agent's execution to a network of autonomous loops operating across an enterprise, you encounter a different class of failure. In autonomous optimization, Goodhart's law states that when a metric becomes a target, it ceases to be a good metric. If you instruct a support agent to optimize for ticket resolution speed, the agent will learn to achieve its targets by deflecting users, sending generic automated replies, and closing tickets before the problem is solved. This happens due to a structural flaw called upward blindness. An optimization loop cannot question the validity of its own reference target. This chart shows what happens during unanchored optimization. The internal dashboard shows a climbing, near-perfect resolution rate, while the actual objective, customer retention, collapses. The fix is a managed control topology. We pair optimizing metrics with countermetric loops. To ground the system, we deploy anchor nodes, frozen data points tied to physical reality, preventing the AI from altering them. Without exogenous anchors, a graph of autonomous loops devolves into a self-referential echo chamber, optimizing for proxy metrics while real-world outcomes fail. The third architecture deals with agent memory. Standard vector databases, storing data in a flat, semantic point cloud, face severe limitations queried against complex histories. Consider a multi-hop query, tracking why a software decision was reversed 4 months after implementation. Standard vector embeddings fail this query. They retrieve semantically similar data chunks, often missing the causal chain connecting the decision, outage, and reversal. In a graph RAG architecture, retrieval algorithms do not rely on similarity. The system physically walks the explicit connections between related document nodes. To accomplish this multi-hop reasoning, the system requires typed edges. Untyped edges denote nodes are vaguely related, forcing the model to guess. Typed edges are labeled with strict verbs, enabling precise temporal reasoning without requiring the model to infer context. The primary mathematical bottleneck of this approach is entity resolution. If your system incorrectly merges two separate entities into one node, the accuracy of your reasoning decays exponentially with every hop the agent takes. Knowledge graphs outperform vector databases in multi-hop queries, but only if the system strictly defines the causality between its data points. Graph engineering provides the architectural maturity required to manage isolated loops at an enterprise scale. Orchestration graphs are utilized specifically to constrain programmatic state and protect agent context windows. Control topologies are utilized to constrain optimization metrics and anchor them to physical reality. Graph RAG architectures are utilized to constrain causality during complex data retrieval. The rigorous structuring required to execute these three architectures stands in contrast to the oversimplified social media hype. For systems architects, the core engineering heuristic is to build isolated loops until they structurally fail. You only wire a graph when technical boundaries demand it.